strict Berkeley time here. It's 1:10. All right. Well, we're pleased to have Dibyendu Mandal here, who's a physics grad student working with Chris Jarzynski at University of Maryland, and they've been doing lots of interesting stuff with nonequilibrium and StatMech, including many different variations on Maxwell's Demon, which is a legitimate topic of study these days. Used to be nowadays we've got experiments that can actually probe molecular scale stuff, and it's becoming a really important area of research, I think. So I'm excited to have you here. Let's get started.
Okay. Thanks, Mike. Thank you all for coming here. So today I'm going to report on a work that I did with my PhD advisor, Christopher Jarzynski. So it's a joint work that I'm going to report on. Okay, so what we did is basically give an exactly solvable model of Maxwell's Demon. I'll explain the terms. And this was kind of missing in the literature, so to speak. Like, people have talked about it, sometimes mostly in general terms, but no one didn't really have an analytical model, by which you have all the different variables and their analytical expressions and everything. So that was the contribution that we made, that we came up with a toy model about which we know everything. Okay. So what is a Maxwell's Demon? So, of course, it's due to Maxwell. So it first appeared in 1867 later to Tate. So he thought of an intelligent being, a small molecular scale intelligent being, which could measure the velocities of molecules and then manipulate their evolution, so to speak. So very roughly, just think of a gas cylinder, which is partitioned into two parts by the central partition. Okay? And there is a small door out there which is being operated by this small demon. So by quickly opening or closing the door, what it does is basically let the fast molecules from the right to the left and slow molecules from the left to the right. Okay? It can do it because it's intelligent. It can measure the speed of the incoming particles, and hence it can open or close that door to let it go or not. So this way it sort of sorts the fast molecules to the left and slow ones to the right. But that really violates the second law of thermodynamics, because by this way we have created a temperature difference between the left and the right. And so we can let heat flow from left to the right, and from that heat we can extract some work. Okay? And we can go on repeating the same thing, and in the process we have created a perpetual motion machine of the second kind. So like, all you need is a reservoir like the sea or the wind, and I can just extract heat from it and convert into work. But that's not possible according to the second law of thermodynamics. So the demon is doing something which is illegitimate, so to speak. But then the problem is, this requires a conscious being, some external intelligent being, and the discussions can become very philosophical sometimes. I mean, what is the demon really doing there? So some people say that the resolution of this paradox comes from the information processing that the demon needs to do. So what is the demon doing? It measures the velocity of the incoming particles. Now, that outcome of the measurement has to be stored somewhere. So people say, well, it measures it, sees it, and somehow stores that information in its mind or brain somewhere. And to apply the conditions of the second law, you have to erase that data that you have stored. And while you are trying to erase it, you need to dissipate heat or increase entropy. So whatever gain you might have had by using its intelligence is now gone in dissipating heat or increasing entropy as you try to erase this memory. So that's the most accepted resolution of the paradox of Maxwell's Demon. So where do we come in? So we say, wait a minute, if information processing is all that is needed to solve this paradox, why don't we come up with a model, an autonomous model, which doesn't have any intelligence, but still can mimic the action of the demon? And in the process, we also expect that all the different parts of the second law that are floating around, that will come into a single picture, because we all know a physical system at least cannot violate the second law of thermodynamics. So on the one hand, we try to show that information processing is all that's going around, and also we try to put everything in a single place so that there is no ambiguity or philosophical problems anymore. Okay, so with that, let me just give you the outline of the talk. First, I will detail the model, and then I'll discuss the results that we get out of the model. And if there is time, I'll go a little bit into the method of the analysis for this particular model and some of the future works that we have in mind or that are going on, and then I'll summarize. So that's the outline of the talk. So what's the model? So the model consists of basically three components. There's a demon. So it's not an intelligent being anymore. It's a physical system, which we call to be the demon. And then there will be some bits. So bits are basically just computer bits, regular bits. These will be two-state systems on which I can store or erase information. And there will be a mass attached to the demon so that we can do work by raising it or lowering it. And in particular, I already have said this, that the statement of the second law that's relevant for our discussion is the Kelvin-Planck statement, by which I said that we cannot have any process whose sole result is to extract heat from one heat bath and convert it into work. Okay? And that's what the demon supposedly did, right there. And all these works are from this particular work that my advisor and I did. Okay, so let's go to the model of the demon. So we model the demon as a three-state system. So the three states are A, B, and C. And this demon is put inside a thermal reservoir. So it can make thermal fluctuations. So it can make random jumps between states, say, A and B or B and C. So like A to B is transition shown here, B to C transition is shown here. However, on its own, it cannot make any transition along the dotted line. So there is no direct transition between states A and C. So that's the model of the demon we have. Okay. So once we have that, as because it's a stochastic evolution, we can write down a rate equation, and the impossibility of this transition on its own reflects by the fact that the rate associated with those transitions is assumed to be 0. And all the other rates are assumed to be unity for simplicity. In particular, please see that because of this restriction, the demon, or which we say the hand of the clock or the dial, cannot make one complete rotation. It will get stuck either at A or C. Okay? Let's go to the model of a bit. So bits are two-state systems, as I said. We call these states 0 or 1. And one can think of an arrow which either can point down or point up. The down pointing state we call state 0, and the up pointing state we call state 1. And what is this red cross here? It means that on its own, it cannot make a transition from state 0 to state 1. Now, you might say, why is that happening? Well, all I'm trying to say is that maybe there's a very high free energy barrier between those two states. So for all the time scales that I'm talking about, this time scale is very large. So effectively, there is no transition between these two states on their own. So that's what I mean by it. Okay. But then, if I let the demon interact with a bit, these restrictions get lifted. So that's the interaction that we are postulating, that the bit can go from 0 to 1 if the demon also simultaneously goes from C to A and vice versa. So it's almost like a catalytic action, like one acting as a catalyst for the other. And that's why, you can write it something like a chemical equation, like the C state of the demon can combine with the 0 state of the bit to go to the A state of the demon and 1 state of the bit, and of course the reverse transitions are possible. Okay, that's the rule of the game. And in particular, now observe that now we can have a complete rotation. So like if the demon starts in state A, on its own it can come to C, So if the bit is in 0, it can then again go to A because of this transition, and hence it can make one complete rotation. Okay? In particular, if the bit is 0, it can make a clockwise rotation. If the bit is 1, it can make one counterclockwise rotation, but not more than one with a single bit present there. Okay, so what happens when we have many, many bits then? So what we do, we bring one bit close to the demon interacts with the bit for a while, and then we get rid of this old bit and replace by a new bit. Now, if all the incoming bits are 0, then for each of them, there's a stochastic possibility that the demon will make one complete clockwise rotation. So if there are many, many of them coming one by one, it can make, at least stochastically likely, that it will make continuous clockwise rotation, right? In fact, that's what you should expect to happen, because it cannot make any complete counterclockwise rotation, and there is a possibility that it will rotate clockwise, and hence, on the average, it does, yeah.
Did I miss when you said, what are the physical meanings of these states, A, B, and C?
So, okay, these are sort of the metastable states of a mesoscopic system, you might think.
Like door open, door closed?
Oh, well, I won't say there's a very one-to-one correspondence between the original proposal of Maxwell's Demon and the model we are proposing. So, well, I cannot say there is a one-to-one connection, like state 0 means door open, state 1 means door closed. No, I won't say that. It's kind of an independent model which does effectively what the original model can achieve, that is simply rectify the thermal fluctuations of a single heat path and convert it into work. That's all, but there is no one-to-one correspondence from the original model to what we are presenting.
There's no intuitive explanation of what is A, what is B, what is C.
All I can say is that we can perhaps cook up, okay, there are 2 or 3 answers to it. We do have a mechanical model in which there is intuitive explanations for these states. So, like, it will be basically, how to say it, a cylinder which rotates. So instead of discrete states A, B, and C, it will be a continuum of states, and the solid line is along which it can rotate, and the dashed line is along which it cannot rotate. So there are situations, but right now I cannot give you one single example which is exact representation of this model. So it's kind of schematic. Sorry.
So I have another interpretational question. You're setting up here, I think, to convert a stream of zeros to work.
Right.
They're not random. So how is this analogy back to the original demon where I'm converting thermal fluctuations into work?
Okay.
You're taking order and turning it into work. That actually, just intuitively strikes me as a little more plausible.
Okay.
Rectifying thermal.
Well, the thermal fluctuations, they do not come from the bits. It's a reservoir in which the whole system is immersed. So it will absorb energy from the reservoir. So it's rectifying the random fluctuations of the reservoir, not the bits. Bits are sort of the intermediate or the means by which it achieves it. I hope it will become clearer as we progress. Okay. So at least hopefully it's intuitively apparent that if all the bits are in 0, on the average the demon will go on rotating clockwise. The whole idea is that now we harness this tendency to rotate clockwise to perform work. And exactly how do we do it? Let me just say it briefly in the next step. So what we do is basically attach a mass to the demon such that if the demon tries to rotate clockwise, say from C to A, the mass will be raised. So you see, the mass is trying to basically act as an obstacle to the tendency to rotate clockwise. So long as the tendency to rotate clockwise is more than the effect of the mass will actually be raised. And that's the whole idea upon which we are actually performing, or we have created this model. So at any rate, we attach a mass such that if the demon goes from C to A, for which we also need the bit to go from 0 to 1, the mass is raised by certain amount delta H. And of course, we also allow the reverse transitions. But because of the mass and the energies involved, we have a constraint due to detailed balance, meaning that these forward transition rates should be less compared to the reverse transition rates, because in the forward rate, I'm extracting energy out of the reservoir, so I'm decreasing the entropy of the reservoir. That's a less likely process. So that's why the rate of forward process is less compared to the rate of backward process, because in the backward process, the entropy actually increases. So that's a more favorable process. And that's the meaning of this detailed balance condition. And we assume that the other rates remain fixed, as we discussed before. So as before, we can write down a rate equation for the joint system of the Demon and the bit. This is now a 6-state system for the Demon and the interacting bit, because the Demon is 3-state, the bit is 2-state, so 3 cross 2, 6. We can write down a rate equation for such a system, and I have written down the rates basically in green along the edges where the interactions can happen. Okay? And in particular, this is the transition when the weight is raised or lowered. Okay. So once we have that set up, we can actually do a little more. So even though it was intuitively plausible that with all zeros we can do some work, our analysis can be more general than that. I mean, what we'll do actually, we'll start with a stochastic distribution of zeros and ones. So the incoming bits do not have to be all 0. Some of them will be 1, some of them 0. In particular, we assume that P0 is the probability that the incoming bit is 0, and P1 is the probability that the incoming bit is 1. Okay? So it's quite general in that sense. And of course, you might guess that, well, if it is all 1, you cannot raise the mass, and we will confirm that. Anyways, so we generalize our analysis to that. And then, from the Demon's perspective, what's happening? So every time period, which we call tau, a new bit comes, it interacts with it, and then the bit becomes old, it gets replaced by another bit, and it interacts with this new bit now. But each bit is kind of the same because they are drawn from the same stochastic distribution, characterized by P0 and P1. So the dynamics of the Demon, in that sense, is periodic, right? Like every time period, it's being subjected to the same condition. And hence, I think it's easy to at least guess that it reaches a periodic steady state, meaning that it will rotate either, say, clockwise or counterclockwise on the average at a constant rate. Okay, that's what we mean. So at any rate, what we do is basically derive an exact analytical formula for this periodic steady state of the Demon and perform our calculations. Okay? And I have just written these two other quantities. So as the bits interact with the Demon, their states may change because of interaction. So the stochastic distribution may change. So instead of P0 and P1, we now have P prime 0 and P prime 1, which characterize the bits that have already interacted with the bit. Because again, the distribution of the outgoing bits need not be the same anymore. And when we have probability distributions, we can calculate Shannon entropy to characterize the information content in the bits. Okay, so that's the complete setup. What are the variables we are after? Okay, so primary variable is, of course, the rate by which we can do work, the rate at which we are raising the mass. And because of the strong coupling between the mass and the Demon, it's essentially the rate at which the Demon basically rotates clockwise, right? So we are interested in a quantity phi, which is basically the average clockwise rotation of the bit of the Demon per bit. Okay, and it's easy to see that it has this formula. Okay. And once we have that rate of rotation, as I said, work is nothing but this factor times the rate of angular rotation, because they are closely coupled. And also we can calculate the change in Shannon entropy of the bits as they interact in terms of phi. I haven't shown the exact formula, but they can be derived in terms of phi. Yeah.
So sorry, Demon's advocate here.
Mm-hmm.
So I guess I'm kind of missing, steeped in Maxwell's picture, I'm missing a feedback connection here. And I would sort of guess that I would put So right, the 0, 1 a string, that's your control signal. That's sort of the model of intelligence or something like that. So Maxwell's demon observes the molecules,
Right.
right? And then, in a sense, here, you would want to gate the AC transition based on some measure of the, now the heat bath is like moving between the states.
Right.
Okay. Trying to rectify that. So based on some, opportune fluctuation, and now I want to ratchet that in.
Right.
This model doesn't have that feedback to the zeros and ones on the tape.
Okay, that's a good question actually. We are thinking about that. Like, as I said, I mean, all you are trying to do is capture the thermodynamic aspect of information processing. Now, to what extent this model can be put in that framework? You see, feedback is a framework, okay? That we don't know. I mean, precisely because we do not have any intelligent being here. So no one is really seeing it, making a measurement, recording it, and giving feedback. No. In fact, that's the whole point of our model, that it's not really a complete feedback system, because a complete feedback system requires an intelligent person to do the feedback. So, but, well, I mean, there are some limits where you can think of it, like when all the bits are 0, then what you are doing is basically the outcoming bits, they have the information about the gyrations of the daemon. So in that sense, yes, you are recording the transitions of the daemon, and hence you are performing like a bit. But I'm not sure if there is a very close relation between the feedback framework and the framework that we are presenting.
Yeah. Can I ask a related question? I don't understand fully the distinction with the feedback. It seems like the daemon in the first case, he only opens the door when there's a fast-moving particle going in the direction that he wants, right? In this case, I feel like this is selecting for the right fluctuations, right? It only opens the door for the particle go in the direction it wants when there's a particle in the door to be, or if you like, it opens the door, but it's not. It opens it at opportune moments when there's nobody there, or when there's the thing he wants there. But it never results in the part. It's selecting for the fluctuations he wants, right? I mean, this thing only allows. Am I crazy? Maybe I'm crazy.
Oh, no, I think you're agreeing with him, and I'm going, wait a second. I expect the intelligent control here to be based on observation of the state of the system, of the thermodynamic system. And I don't see that here. I put all my zeros down, and yes, I'm driving this little ratchet, and I'm going to pull out the thermal fluctuations, and even because it's rotating one particular way. I got that.
But the thing is, all the operations here have a handedness to them. So like the original picture with the daemon, he doesn't have a filter that goes one way or the other. He just opens the door. In this case, there is no opening a door. There's only opening a door that only allows things to go that way, or opening a door that only allows things going that way. So built into it is a handedness, right? The fundamental operation is different.
Well, it seems like really the operation of the daemon here is the reset, because that's what allows this to continually do work. Is every time you put another 0 there, you start at the top of a hill again. And that seems like a sort of different mechanism. Rather than talking about Maxwell's Demon, let's talk about Szilard's engine. You do a measurement to see which side of your box you have a particle on, right? And then based on that observation, you make a choice for how you're going to expand your box. Here, you just do the same reset every time. There's no necessity for a choice. You're just putting it back on the top of the hill, and that's what seems qualitatively different. There's no choice that seems to be made by the daemon, depending on, I guess, what you define as the daemon. But I sort of see them as being distinct in the way they operate also.
Yeah. Well, as I said, I mean, there is no observer, there is no intelligent being in our model, and kind of that's what we wanted to do. We didn't want any intelligent being or any observer, because we want to prove the point that, whatever it is, it's all about information processing, and that's what we are doing here.
Well,
So
I'm happy to have a proxy where the thing that's putting down the control, zeros and ones, is some finite state machine, and a push-down automaton or a Turing machine. And that allows me to start modeling intelligence. That's not human intelligence, but you're right, that should just take that off the table. But there's some sense of measuring the capacity of the information processing with these different models that could lay down different protocols.
So you are meaning like who is determining these initial bits?
Yeah.
Okay, I understand your
Some
point.
sensory apparatus that
Yeah,
goes down,
okay.
And then there's a Turing machine or finite state machine that then goes, oh, okay, fast molecule coming, or I'm in now state C, I should let it go across because I decided to go counterclockwise.
Okay.
If you were trying to build this physically, you'd have to give state C a way to tell a 0 from a 1, right? And isn't that a binary, not human intelligence, but it's a binary?
Roughly speaking,
decision.
yes. Like
And
C,
that's where the
yeah,
entropy.
yeah, like
comes
C.
in.
I think is this what you're trying to say? Like C is the state 0, and hence yes, I will fluctuate that
Yeah.
way. And A sees 1. Okay, I should fluctuate back that way.
Yeah.
Yes, but again, it's not an intelligence choice in our model because it's built
define
in.
intelligence, but it's not living. But
Yeah. That's what I mean. Yeah.
But it's still a binary
Yeah.
decision.
Decision. Yes, you can see it that
With
way.
every binary decision, there's a change in entropy.
Well, how do I put it? So, given a state 0, it has to go to, say, what was the rule again? It has to go to A. I mean, it doesn't have any choice. So, it's not really a decision, because in decision, you have a choice. Okay, I am in state C, and I have a choice. I can either go here or here, and then I'm making that choice or decision. But here, it doesn't have any capability to make a decision. It's kind of the physical rule. I mean, if it is 0, then if it goes 1, you have to go to A. It doesn't have a choice there. So I'm not sure if I should call it a decision making. Okay. And so anyways, we are looking for the rate of work that is delivered by this system and the change in information entropy per bit, because we have this preconceived idea that they must be related. And so what are the parameters in the problem? So by the way we have set it up, we have 3 parameters. The first is the delta. So this is simply the excess proportion of zeros in the incoming bits. And we have already discussed the case where delta is 1, meaning that all of them are 0. And so if delta is 1, we do expect that the setup will act like an engine, meaning that it will raise the mass. And the second parameter is what we call epsilon. It came from digital balance. One can just think of it as a rescaled mass. It's just the effect of gravity. The more the mass, the more the epsilon. The less the mass, the less the epsilon. That's it. And the third parameter is the duration for which the daemon interacts with each bit. Okay? So, like if this duration, which we call tau, is very large, then the composite system of the daemon and the bit have sufficient time to reach equilibrium. But if tau is small, then they will remain out of equilibrium. So if tau is small, the steady state or the periodic steady state that I'm talking about is really far from equilibrium. Okay? So what I do is basically calculate these 3 quantities in terms of these 3 parameters in the periodic steady state and see how my system behaves. Okay? In particular, if W is greater than 0, it is delivering work, etc., etc. Okay. So we go to results then. Just to show you that we have actually done the calculations, that we have calculated phi in terms of these parameters. These are not too complicated functions. And then once we know phi, we know work in terms of this formula, or we know the change in entropy in terms of this formula. So yes, we have the results. Okay. And perhaps I'll bring your attention to just one particular fact, that if I look at the clockwise rotation that's measured by phi, then it has this rather simple form, I would say. There's this prefactor, which is proportional to delta minus epsilon, and there is some complicated quantity. However, I can prove that it's non-negative. So the sign or the direction of rotation is determined by just the prefactor. And what is that prefactor? You see, delta kind of measures how much more zeros I have. So that's like the force due to the information, so to speak. And epsilon is the force due to the weight. And there's a competition between them. If the force due to information wins, then it's clockwise. If force due to the weight wins, it's counterclockwise because it's negative then. So that's kind of one physical picture to have in mind for doing at least qualitative analysis. Okay, so I have just written here, so delta or excess zeros favor clockwise and epsilon counterclockwise. Okay, so what do we discover after all these algebraic formulae? So what we do is basically draw a phase diagram. I'll come to it. And in the phase diagram, we actually discover different regions. So it's not engine everywhere. It can actually function at different purposes. So let's see. So we observe that if we plot, say, along the x-axis, the excess proportion of zeros or delta, along the y-axis, the epsilon, which is again just rescaled mass, and say fix tau to be unity for simplicity, then we get a phase diagram, by which I mean in different regions of the two-dimensional plane that we have out of these two parameters, the model acts as different or serves different purpose. So there is a region here where it acts as an engine, by which I mean it actually raises the mass continuously. And as promised, if all of the incoming bits are 0, that is along this line, and the weight is positive, then it always raises the weight, whatever be the magnitude of the weight. So at any rate, this result is more general than that. We can have an arbitrary distribution of the incoming bits, and that's characterized by delta, and we discover this. Just to give a little bit of flavor of how we are using the algebraic formulae that we derived. So this is the formula for phi that we just discussed, and this is non-negative. Work is this. So we can check that the sign of the work, I hope it's visible. Is it visible? Okay. The sign of the work is basically the sign of the product of two factors. Okay, that comes from these two formulae. So like in this region, both these factors are positive. They mean that the mass is positive and or the weight, okay, anyways, I won't go into that. And the force due to information is more than the force due to the weight, and hence it acts like an engine. And because both of them change sign in this region, again, it acts like an engine. It's like connecting the mass the other way around and having, instead of all zeros, you have all ones, but of course, it's a symmetric behavior. So that's what reflects here. And let's go to the other region then, eraser, because we haven't talked about it here. So what does it do? So eraser is the case where we're decreasing the information content of the bits. So we start with some stochastic distribution characterized by P0, P1. We calculate the Shannon entropy per bit from that distribution. After interaction, they have a different stochastic distribution. We calculate the Shannon entropy for this after interaction distribution. If the second after interaction distribution has less Shannon information in it, I would say, well, then information has been erased, right? So in that sense, we call it an eraser, that the final entropy per bit is actually less than the initial entropy per bit. Okay?
I have a question.
Yeah.
So if the bits coming in are independent.
Yes, I should have said that explicitly. Yeah.
Well, you said bias coin.
Yeah.
Are the output bits uncorrelated over time?
No,
Okay.
they are correlated.
So
Yeah.
how are you going to measure that change in temporal correlation of the output?
Great, great. Okay. Firstly, I'm neglecting that here, but you can take into account the correlation into picture. And even then, of course, you can recover the second law. So like while calculating the Shannon entropy per bit, we are neglecting completely the correlations that the bits might have developed during the course of interaction, especially for finite time. And even if you take that into account to calculate entropy, of course, you recover the second law. But I'm not going to talk about it here.
How
Okay.
exactly are they correlated?
That's interesting. So you see, in finite time, how do I put it? Okay, so take the demon and take the bit. They interact with it, so their distribution is really correlated, right? It's not a product state of the bit distribution or the demon distribution. and then you quickly replace this bit by a new bit. But the daemon has memory of the old bit. So when it interacts with the new bit gets some information of the old bit via the daemon. So that's how they become correlated. So yeah, that's a good question. Thanks for asking it. But we don't really explore it here. And anyways, I mean, for the parameter region that we are exploring, the amount of correlation that develops, it's really very small. Okay. Fine. So what you do again is go to the phase diagram formed by this x's parameter and mass, and again tau is equal to unity. So if we look at again the mathematical formulae, we see that the sign of change in information entropy neglecting correlation, because if we take correlation, this diagram will change a bit. It's again a sign of a product, namely the current and delta minus phi, and then you can actually effectively find out the regions from their formulae where the information entropy of the bits is actually decreasing, and that's this region. Now, sort of taking cue of that question, as you might have guessed, time might play some role here, because all the phase diagrams that I have shown, they are for tau equal to 1. What happens when tau is greater than 1, say 10? Okay, let's go to that. So we see, so here I'm comparing tau equal to 1 with tau equal to 10. Okay? The engine region, as it turns out, doesn't get affected. That remains the same. But the eraser region does get affected. In fact, let me make this just comment, that if tau is very small, meaning that it tends towards 0, then this line, it actually tends to this white vertical line. Okay, that's kind of also apparent from this picture. And when tau goes to larger and larger value, this left boundary of the eraser region, that approaches this opposite diagonal or epsilon equal to minus delta line. Okay, and that's just because for finite time, the bits do not have enough time to change their statistics much. Okay, it's the effect of that time. Okay, but I won't go into more details than that. So what do I want to do? Yes, the second task, like what is the form of the second law in this case? Because in the original formulation, the daemon violated the second law, and you had to incorporate all these information things in its brain to recover, so to speak, the second law. So what do we need to do here? It's more or less apparent by this time, but let me still say it. So if we use those formulae that I just showed, we can check that this inequality holds. What is it? So the change in entropy of the bits minus the work that we get in units of the thermal unit kT, that is greater than or equal to 0. Okay? Now that shouldn't come as a surprise, because where is the energy for the work coming from? It's from the reservoir. So if you are doing some work, you are extracting heat from the reservoir, and hence from Clausius relation, you are decreasing the entropy of the reservoir. And hence, that W is nothing but minus kT times the change in entropy of the reservoir. Okay? So if we plug it in here, all it says is that change in entropy of the bits plus change in entropy of the reservoir, that's non-negative. So that's the usual form. So what's new here? The new thing is that this is really physical entropy. In a sense, we can calculate it using Clausius relation. This is not really a physical entropy. It's more like Shannon information. And all we're trying to say is that Shannon information or Shannon entropy is not really very different from physical entropy, because you need to take into account to recover, so to speak, the second law of thermodynamics. So it's almost on the same footing as physical entropy. That's what we're trying to say by this relation. Okay? So in any physical process, not just the reservoir, but the bit, in total, they will change their entropy by non-negative amount. Okay. So we can just look at each of the regions in detail. So in the engine region, work is positive, but you have to increase the entropy of the bits by more than equivalent amount so that the second law is not violated. In the eraser region, you are decreasing the information entropy, but you have to supply work so that it converts into heat and goes to the reservoir, and hence the sum remains again non-negative or positive actually in this case. And there is this white region about which I haven't talked anything. That's because we don't find that region very useful because it doesn't perform work, it doesn't erase memory. So what happens is that both these entropies are positive. So we just call it dud because we don't have any useful name for it. Okay, fine. So that kind of summarizes the results, and I think I have some time, right, for the methods?
Yeah.
Okay, so let's go very quickly to how we actually do those calculations of the formulae that we had shown. Okay, so it has basically 3 steps. Okay, first we have to find out the periodic steady state of the demon that I talked about. I'll change the notation later, but that's the idea. And then in that periodic steady state, I have to calculate the statistics of the outgoing bits, because from that I can calculate the change in Shannon entropy. So that's what we do. And basically we use this formula that I had actually shown before to calculate phi. Okay, so all I'm trying to say is that it's a 3-step calculation. We find out the periodic steady state of the demon, we find out the statistics of the outgoing bits in this periodic steady state, and that gives me phi by this formula. Okay, and let's go to the first step. Okay, what happens at t equal to 0? Now let me actually go to notation first. By PD, I mean stochastic state of the demon. I use boldface because it's a 3x1 probability vector. Okay, and by PS, I mean periodic steady state. Okay. Fine. And so in simple, it's PD at 0 means the stochastic state of the demon at time t equal to 0. So that's kind of the notation here. So at t equal to 0, there was some initial state of the demon. We don't care about it actually. And the first bit comes in and they start interacting. So what's the joint state, which we denote by PDB? So D for, again, demon, B for bit. So that is basically given by this state of the demon times the product matrix, where the matrix carries the information about the stochastic state of the incoming bits. And so that's how we get basically a 6x1 state vector for the joint state of the demon and the bit. Okay, what happens after that? For the next time interval or time period, it evolves according to the rate equation that I had shown for the 6-state system. So this is the equation, and I give the elements of R, and the solution is, at least formally, is given by this. You have to exponentiate R times tau and just multiply the initial state. Okay, and what to do if I want to find out the state of the demon only at tau? Well, we have to project out the state of the bit. So I have to find out a projection matrix which projects the joint state of the demon and the bit at time tau to the state of the demon. So that's what is done by this matrix PD. It's simply basically a 3x6 matrix, and that's given here, where I is simply, I should have written it here. I is this 3x3 identity matrix. Okay, so we start with the demon, multiply it by m to get the joint state of the demon and the bit, evolve the joint state, and subtract or say project out the bit degree of freedom to get again the state of the demon. So I can write it in a very compact form. So if I know this matrix T, which is simply product of this projection, this exponential, and this multiplication, then if I simply know this, I could have inferred this final distribution from this product, which we call T, or transition matrix. So that's what is important, because if I want to calculate, say, the state after time n tau, it's simply the nth power of that transition matrix multiplying the initial state of the demon. Okay, on top of it, as because it's a positive operator, there are theorems for it. One can check that if n is very, very large, like after sufficiently long time, whatever be our initial state, the final state is basically the steady state solution of this transition matrix. Okay, that's what they call Perron-Frobenius theorem for positive operators. It's a standard result. Okay, so that's why we took trouble to define this transition matrix, because the periodic steady state of the Demon is simply eigenvector of that transition matrix with eigenvalue unity. Okay. So what do we do then once we have the periodic steady state? Well, we start with the periodic steady state, joint it with the bit, evolve, we have the final 6-state system, but we want the bits now in the second step. So instead of projecting out the bits, we project out the demons. So that's what we do here. We multiply, we evolve, but this time we project out the demon, so we have a different projection matrix which is given here, and hence get the statistics of the outcome. You know, when intelligently inventing one resetting mechanism, you can mimic the same thing, but in the process, you must be writing information somewhere.
Well, by the second law, yes, that would
Yes.
be true, but one would hope that you could illustrate why that has to be true.
Frankly, okay, it can become philosophical a bit. One might say, wait a minute, are you trying to prove the second law? No, wait, I'm not proving the second law. Why? I'm taking Markov assumption, and any Markov process will satisfy the second law. So no way, I'm not proving the second law. In fact, all the proofs that I talked about, that even when they are correlated, they come from the property of Markov process. So no, I'm not proving the second law, no. It's an illustration in a clever setup, you might say, but it is not a proof of second law.
And I'm talking about, you said you had a mechanical, sort of way. I just want to understand if I'm understanding it. So if I give you some ID bits, okay, with not, with some entropy or whatever, and you're telling me I can create work. That's what you're saying.
Yeah.
Okay, I just want to make sure I understand. Okay.
Yep, that's Landauer.
So,
There's a minimal amount of
Okay.
bit per bit. It's kind of down to bit per joule, isn't it?
well, this is what I will add to it, that, see, information is not getting converted into energy, no. Information is the means by which you are taking energy from the reservoir and convert it into work. So don't make at least connection that information is energy.
No, I'm just saying I give you a sequence of bits, like
Yes.
ID
So
bits.
if you give me
Here they
all
are,
0 bits
some
set,
mechanical instantiation of that
I
handshake
can
or whatever it is.
get work out.
And you're saying that's what I'm okay.
That's the basic picture.
But Landauer's principle is that it takes a certain minimal amount of energy to erase a bit,
Yeah.
right?
Yeah, so that's what is here actually. Sorry, I'll go very quickly. So in the eraser region, I didn't say, sorry, I should have said his name at least, because that's how we got into it. So you will see that you can erase memory, but you have to do work by more than the equivalent amount. So this is actually Landauer's principle.
Yeah.
Yeah. I mean, there can be some other discussions about different measures of information, which is not Shannon information, but that's really separate. That's not part of this work.
So in order to do work, it seemed to me like in order to lift a mass of anything greater than 0, you needed to have some difference between the zeros and 1s, right? You need 51% zeros.
Yeah,
or something.
exactly. Yeah.
So, but if you have truly sort of random zeros and ones, it should be in the infinite regime, or if you have enough of them, you have exactly 50%, no?
Mm-hmm.
So then, aren't you taking some thing that isn't really random, right? In order to do work, you need some stream of bits that is not actually random. They already have some information in them. Am I understanding that right? They already have something in.
Yeah. So when we say that I am not taking delta equal to, say, purely 1 or -1, I am allowing zeros and ones on the bits. So yes, they do have some information. So again, we don't have to have just a bit stream with all zeros, no. Some of them can be 1, some of them can be zeros, and we can still do work, and that's the whole point of this phase diagram. That even when delta is not equal to 1, that is not all of them 0, we can still get work. So yes, some pre-information is not a problem so long as it belongs to this phase. Is that the question?
I think so. Yeah, I think so. I mean, so you have maximum entropy when you have a string of zeros and ones that are half and half, right?
Yeah.
So already you've got.
Yeah, then you cannot do anything. That's precisely this point. Yeah. Because you cannot increase the bit entropy anymore, and hence you cannot use it to perform work. And that's why basically this point does not belong to the engine part.
Okay. Yeah. Okay. I guess I get it. That in the engine regime, what you're doing is extracting some entropy from the bit.
Exactly.
To do work. But the bits are not actually doing work. They're sort of the mediary between your heap bed.
Because the whole point is that second law puts this restriction and nothing else. So we are just utilizing that restriction.
And so you're creating work, but you're actually extracting more energy than the work you're creating.
Work means extracting heat and putting it into a systematic form, like raising the mass.
But this delta SB is the
Change in entropy of the bits.
and that's higher than the amount of work that you're doing.
Yeah.
So you're not gaining. You're still losing.
That's the whole point. That's the whole point of the second law. You cannot beat it.
Yeah. Got it.
Yeah. Let me ask you some more questions. We'll do it out. All right. Thanks a lot.